Today we're going to be looking at FRC prototyping, the concept behind why we prototype, kind of the different levels that we go through in the prototyping process and where we prototype along the design process. We're also going to be looking at some of the reasons and details of what we're trying to figure out with the prototyping, some of the tools we use while prototyping, and then we'll look at some examples at the end. When we talk about prototypes and we talk about what is prototyping, there's a lot of different sort of things that get thrown around as this is a prototype, this isn't a prototype, whatever it is in FRC. The definition I want to use today and what we're just talking about is anything that we build that isn't intended to be on the final robot. So anything that we build that's not going to be on the final robot, that's not intended to, that's its point. Like sometimes we'll build something on the final robot, it doesn't make it there because we either decide not to use it or it gets replaced by a better iteration. Those aren't what I mean. I mean things that we intentionally know we're going to build with the sole purpose of it never seeing the actual FRC field. And the reason we build these things is so that we can get more knowledge and more information about the problems that we're trying to solve. So it might be as simple as something like this tape measure extender that was going to figure out whether we could make like a tape measure climber for some year, or I think it was an extender maybe from 2015. I don't remember exactly what it was. But it was a prototype. It definitely, that piece of plywood was never going to see the competition robot. And there's a bunch of different levels of prototypes, anywhere range from something like this to something more complete that looks closer to a robot, to something that very much looks like a competition robot, but is still not built to actually see the competition field. So kind of listing the way that I break them up, or that we break them up over the years, and kind of how we've kind of spliced them into these 5 different categories of prototypes. So we have our concept prototype or concept test, and these often aren't even like full mechanisms. They're just us trying to play around and learn about some problem from the game, or maybe how the game piece interacts in some way with wheels or other game pieces or whatever we're trying to do. An optimization prototype is built specifically to sort of solve or to find the right range or solution to values that could change in a concept. So if we have a launcher and we're trying to figure out different types of wheels, maybe wheel sizes, widths, compression to whatever the hood or other wheel is, velocities, anything like that, where there's a bunch of different variables or settings that you could put into your final product, the optimization prototype is there to kind of help you tune and tweak the mechanical properties to get the outcome that you desire. A single system prototype is where we start getting things much closer to an actual competition mechanism. So they're going to look very similar to the mechanisms that we have on the robot. A integrated prototype is where we take multiple of those mechanisms and test how they interact together. And then finally, we have a prototype robot where it's going to be pretty close to a fully functional robot. It's probably driving around. It's going to look very similar. It's just made without the same materials and to the same standards that we're going to use on the competition robot. So the first thing we want to look at is our concept test or concept prototype. And these are, again, very, very quick to build structures or mechanisms or tests that don't take much time at all. We're talking an hour or two. They're definitely not. It's not a multiple day thing to build a concept prototype or a concept test. You kind of get in the lab and you decide what you're trying to learn, and you piece something together to do it. We're probably drawing on the whiteboard, and we're not using a lot of CAD to do this. There's not a lot of precise dimensions to do this. It's a tape measure, whiteboard drawings, and whatever we have lying around is a lot of what we're doing. We're probably not ordering parts very often, or unless we're concept testing a single part that we ordered to see if something works. Most of the time, we're just learning with what we have and learning about the game and the objectives that we're trying to do. They're not designed to be easily adjusted. Like they might be able to be. Like maybe if it's not quite working, we could move a motor out or something, unscrew it, screw it back in a different spot. But they're not intended to give us very precise measurements in any way. The example we have here is our 2013 Frisbee launcher. So this is just a bit of plywood, some motors, and wheels. And this allows us to just see exactly how a frisbee launcher would work with these smaller wheels. We hadn't seen a lot of other teams do it. We didn't know if it was going to fly far enough to make it work. But we had some concepts, we had some ideas, and we wanted to test them very quickly. And some pieces of plywood, wood screws, a few bolts, some Lexan Velcro tape, any of that sort of thing can get us to a concept and kind of we're going down the right track. It's kind of all we're trying to figure out most of the time with the concept prototypes. Optimization prototypes are built specifically for allowing us to adjust variables. So this is where we take a lot more time to design it. So this is we're going to put more time into CAD. We're going to think really clearly about what we want to know about the problem. We've already learned some things, or we already have some feel and knowledge about the problem. Maybe it's launching balls. We don't necessarily need a concept prototype for that. We know how balls launch, but we don't know how specific balls launch with specific wheels and specific spacings and RPMs and anything like that. So we can build up a structure that allows us to quickly change and modify our prototype to allow us to test a lot of things very, very quickly. And that's what the goal of the optimization prototypes are. This example here is a 2016 optimization prototype that we built based on a design by 2848 that they shared with us. It allows us to change the wheel sizes, the wheel spacings, allows us to change the compression of the ball, the types of wheels. It wasn't a perfect system. It still took a while to get the next iteration done. So some of the other tools that we have now are there intentionally to try to make some of this process faster to both build these and get the most out of them very quickly. Anytime that we're spent kind of adjusting the prototype and working on the prototype, we're not really learning about the game piece being launched and actually doing the testing. And that's the whole point of the prototype, is to actually use it and run it and test it over and over again and learn from it, not just fiddle with it specifically, because that, again, the prototype's never going on the competition robot. We're not worried about if the prototype works. We're just worried about getting knowledge and information from it. So we need it to work for as long as it can and be functional and be ready to go to test the next thing very quickly. So that's a lot of our goals with the optimization prototype. Okay, so single system prototypes are basically the first iteration of the mechanism or the subsystem for the robot. The goal here is to test out kind of what we learned from either the concept prototypes or an optimization prototype if we did it, or just some of our design choices that we've made already. So if we've been doing some amount of CAD, we've been kind of playing with how everything's going to fit together. And here we're going to try to relatively quickly build up enough structure and parts of that mechanism that we can test it and the actual real geometry relatively fast. So this was our 2019 cargo intake single system prototype. So this is just the intake. This whole mechanism was planning to be mounted, like on the real version, would have been mounted on an elevator. It would have had like its own tilt mechanism in here on the real version. So we designed it to when we assembled it, it was at the correct height, like whatever our lowest height we thought it was going to be at from the floor, like in CAD. And then also at the correct tilt from how it was going to tilt with the wrist, so that we could model how the ball would actually intake. So we actually used a spare bumper from a previous robot. So we can get the exact idea of how the real system's going to work without having to spend as much time machining the real materials, the real motor placements, all of that. So like this motor is sticking out the backside here, which is not how we do it on the real robot. We'd like flip it around and tuck it under, but it's a lot harder to design that. It needs more parts, so you don't need to do that in this prototype. We even like had this one use pneumatics, so we were actually able to lift the arm up and down in the same way the pivot would work on the real robot, so all the same geometry. But we could build this over the course of a day, maybe two after school, instead of the multiple days it would take to build a real iteration, and much more expensive to build a real iteration out of all of the correct plastic and everything else. So we can still learn all the concepts without having to spend as much money and spend as much resources and time building that. We also, because we know it's a prototype, it's a lot easier to be like, oh, this isn't working. We can just drill random holes in it, and we know it's not going to stay together more than a few days, maybe a week. Modifying it, making new parts for it can all be really quick and easy, and we can just get to the point of where we're happy with it and we know it can work, and then we design it up into the real version that'll go on the robot. The next type is an integrated prototype. So this is where we're looking at multiple systems working together and how those things interact. So back here, like we said, we didn't have this like risk mechanism that we'd have on the real robot. We didn't have the elevator. So we couldn't test how those would interact with this prototype. In 2018, we went a step further. So this isn't quite a full robot. This is definitely just a mock-up, but it gave us an idea of how our intake prototype, which is made out of plywood, was going to actually interact with being mounted on the arm and the exact angle it would be approaching the cubes from. We could push it around so it was on wheels on this like 2x4 frame. So we could drive it into the cube. So we could see, okay, as the wheels are spinning and a cube is positioned like this, how well does the intake grab it? If the cube's in the corner of the field, can we still grab it? If the cube's like this, if it's against a wall, if it's in the open field, like we could test all of these scenarios early without having to have a fully functional driving robot, just by pushing this around, having the motor spinning, and seeing how it worked. The arm could be manually tipped up and down, so it was on a pivoting axle. So we can move the arm up and down and see, okay, if the intake's here, can we get it up and over the scoring location it needs to be in? So we could do all of those things relatively fast with basically just 2x4s and stuff we already had lying around the lab, plus our actual laser cut designed prototype intake with all the geometry that we were working on. So the same thing could be done if you needed to do it, like I said, with like the ball path where we go from intake to the indexer or serializer or anything like that, or indexer out, anything where we're trying to figure out how two of our subsystem or mechanisms interact together, you can make a prototype like this. A prototype robot is the furthest step. So this is a step that not every team does. We'll do it some years more than others, or we'll worry about it some years more than others. Recently, in 2020, we had a prototype robot mostly because with no bag and the way that the season worked out, it made sense to put some more time into building this prototype robot that wasn't done exactly to spec, but was very close, but was definitely a lot cheaper to build, so that we could iterate on it very quickly. And then once we had the competition robot and we were able to build that up as we got closer to our event, the prototype robot in the season we would have converted to being almost identical to the competition robot. So there was enough stuff between them. There were enough things we knew that weren't going to change. So it was really just mostly the panels and things that were cut out of wood that would have all been changed over to plastic like they are used on our competition robot. And this would have become our practice robot. So they would have been kept identical after a certain point once we got this one up to the competition spec. And then throughout that season, we would have been able to do new iterations and things on the practice robot before moving them to the competition robot. We could have also done driver testing, autonomous testing, or driver testing on the practice robot. Auton testing, for a variety of reasons, stays on the competition robot because it's really important to get all of the settings right. If there's any minor differences between them, you want to make sure you're tuning and tweaking correctly for the competition robot. This one didn't have the climber on it. We had another like chassis that we built up just for climber testing and form mounting and everything. So that was useful, so that we could be working separately on the ball mechanism stuff over here, and the other group could be working on the climber test chassis build up in a different place. So a lot of it is sometimes like space and just how many people and time you have to be able to get everything done. Yeah, one of the biggest things is basically nothing. We don't care a lot about things looking nice on any of this types of prototypes, especially this robot. This is more about getting it done quickly, learning as much as we can, so that our first attempt at the competition robot is as high quality and has as few problems as we can get it in the time that we have. Okay. So let's talk a lot about why we build prototypes and what they, their actual purpose and what they allow us to do. So I'm harping on it a lot because it's very easy, and we used to do it a lot, where we would build prototypes that weren't necessary or didn't actually help us in the season. Um, so one of the first things is that not everything needs to have a concept prototype. A lot of times as a team, we're going to understand a problem well enough that we don't need a quick concept prototype to know something is going to work. If we get another ball launching game, we're pretty sure that a spinning wheel is going to launch the ball relatively well. I don't really care what ball it is at this point. A spinning wheel is probably going to launch a ball pretty well, if around a spherical ball. We start getting into footballs and things, it gets different. But we might need to do a concept prototype for something like that. But any spherical ball, we probably have a decent idea of how we can get pretty close to either an optimization prototype or a single subsystem, single mechanism prototype without having to just strap a wheel to something and seeing if it shoots the ball out, because it probably does. Elevators are another example of this. It doesn't really help much to build some sort of wooden elevator thing that sort of kind of slides around for most things that you're prototyping, right? Unless there's a reason why you need to test something else. Maybe it's part of a integrated prototype where you have a weird wooden elevator or some other quick elevator that you put together that you're mounting your intake or something to, because that's important for understanding the geometry of something else or how they interact. Just understanding how an elevator works, you probably aren't going to get much if you're not building it pretty close to the spec of a real elevator, just because so many of the things rely on the bearings and friction and everything else that goes into them. So a lot of times you end up it doesn't make sense to prototype it. It makes sense to figure out the variables involved and make a real first iteration of the design instead of just doing the concept. The other suggestion, and this is more for other teams, but sometimes us as well, if you have limited resources, most of the time we shouldn't be wasting them on prototyping. So if we're worried about time, or we're worried about money, or we're worried about anything else, the prototyping phase is not always, the concept prototypes especially, are not the place to worry or to put resources if it's going to make it to where it's impossible to have your end product, the one you actually put on the field, if it's going to make that any worse. So a lot of times, if you just don't have the resources to prototype, whether it's time, money, knowledge, whatever it is, figuring out how to get your first design to be better and using something like another team's resources where they've prototyped, using examples that they'll post on YouTube or Chief Delphi or Twitter, Facebook, whatever, wherever teams are posting their content, you can learn a lot about the same problem, since all, 3,000 plus FRC teams around the world are solving this problem at the same time, or solving a lot of the same problems at the same time. Each individual team doesn't have to be the one that prototypes. The Everybot is a really good resource that they go through. They do a bunch of testing and prototyping, and they release a whole robot design. The different Robot in 3 Days groups do a lot of different prototyping and things that you can see and watch videos from. A lot of teams will post them. So there's a ton of way to get the same information about the problems we're having to solve without having to do it yourself. It is very important to know the very specific goal for the prototype that you're building. We need to know exactly what we're trying to learn from building the prototype. So if you just build it because you think it's the right thing to build and you can't actually take any information from it, it doesn't actually help you, right? So prototyping is kind of the point where we get similar or closer to like the scientific method, where we're going to have a hypothesis that says, okay, we think that intake wheels of this size and this location is going to intake the ball well, or intake the cube properly, or not going to get jammed in this way. And so that's what you're trying to like figure out. How do you build your prototype and test your prototype in a way that can actually confirm or reject your hypothesis, right? Like, is it going to, can you build it and test it to where you're like, oh, we're going to try to stop ball jams from happening. You need to make sure you put a lot of balls in like every orientation you can and try to make it jam to make sure that's the part that you're actually testing. If you just test it in the most ideal scenarios and you're like, hey, look, it works. You're like, yeah, it works there, but is it going to actually work on the real field? Are there things you can do to improve it before you build the real version? And that's what we're really trying to figure out with any of the prototyping we do in the season. This is one of the most important parts of just any part of the design process in general, is we have to know our constraints. So this is the game and robot rules. This is why we spend the entire first day reading over the game and robot rules to make sure everybody understands them. This is why we harp on them and bring them up and have them displayed all the time, and we reference them throughout the year. No matter how cool of a concept it is, no matter how well the prototype works, if it's illegal because of the game or robot rules, it doesn't matter. So we have to know, like, that those are the most important constraints. Those are the specs we have to build to and be confined to. If we do not do it within those, none of our work will matter because we can't actually field it. It's not going to get us points. It doesn't help us win matches. Doesn't help us win events. All of those things. We have to know the constraints of our time, our schedule. Does this concept make sense to be able to be built? Like, maybe this is a really great concept, but does our team have enough hours in the season between all the people capable of implementing it to actually do it and do it well? Is it going to be the best option of the variety of options that we have to actually do it? Is getting the exact right dimensions of this prototype going to take too long to where we're going to be past the time where it's useful to have it for events or anything like that? Packaging constraints are ones that we somewhat get to decide on. So part of it is robot rules. There's an overall robot volume that you can't extend past. You have to build within at the start of the match. Sometimes you can expand a little bit, but you still have to be within some overall volume in most games that your robot has to stay in. And within that, you then have to figure out how much space is allocated to each of our subsystems or mechanisms. And part of that needs to be known partially before prototyping, or at least have an idea, general range of, okay, there's going to be an elevator on this robot, therefore the intake can't take up the entirety of this whole space because somewhere an elevator has to be mounted. Thinking about the other subsystems and how they're going to be attached to the robot or to the rest of the robot, to your mechanism or to the mechanism you're prototyping, all of that matters into making sure the prototype that we design is going to be, again, actually functional and useful to our overall concept. Weight matters. We don't want to be building. A lot of this is just stuff that happens within the constraints of our overall design, but they are important in prototyping. Is something going to be too heavy for the robot? Is it not going to be robust enough? Like, what kind of materials are we able to use to prototype it, but then how does it translate to materials we'd use in the actual robot? Like, it's important to know if there's going to be some big differences there. Maybe it's going to change things. I have an example about that later when we talk about our 2020 shooter prototype. How many motors and pneumatics can you use on a mechanism is going to be really important, because if your prototype indexer used 7 motors, and we definitely didn't have 7 motors available to use just on the indexer, no matter how good it is at sorting balls, it doesn't actually matter because, again, can't put it on the robot. Tools is more, don't design anything, prototype or not, that we can't actually build either in our lab or in the resources we have available to us, whether that's asking other teams to do it or our sponsors or whatever it is. But if we have no way to actually manufacture something, and it could be a really cool design, again, if we can't do it, it doesn't really matter. So all of those types of constraints are important when we're just, how do we actually build a thing that can be useful and that we can use to make the robot better? Learning before we start. So it is important and much more efficient for us to go out and learn about the problem before we try to start completely from scratch. We don't need to reinvent the wheel. We are doing a lot of the same tasks and problems that teams have done before us. Some of the teams will even do them in the same year, and they'll publish them, like I talked about earlier, when there's YouTube videos and everything else we can go find. looking at the examples from past years, looking at the examples from the current year, anything we can get that can make our first iteration of a prototype better is going to be useful to us. So it's time well spent to do some research before we go and just start putting in hours building a prototype, because the solution might be out there already, or a more interesting solution, or something that might just be um, a little tweak or something that gives us an idea of something else that we want to test. Be like, oh, this worked for the 2018 Power Cubes. Maybe if we modify it a little bit, it'll work in a similar way for whatever the next game piece is going to be. So anywhere we can just gather more data, more information, more knowledge that can inform our future designs is always a plus. There's a lot of published examples from the current years. Those are some of them. Also, another thing that we do is we talk to quite a few other teams. So there's teams locally that we talk to regularly that we're just talking about how they're working through the problem. There's also teams that we chat with from all over the world that we chat with regularly about what they're doing with robots, sending pictures and video back and forth and things. And so that gives us a really good idea of kind of how other people are approaching these problems and what we can do to possibly shift our design choices. Maybe like maybe our prototype's not working very well and we're like, oh, that's not picking up the ball at all. There's other teams is, let's build a version of this, tweak it a little bit to be closer to how we build things in the space and allotment or allocation that we need for our robot, and see if it works. So we can get those ideas from a lot of places. It doesn't just have to be something that we thought of. We're just trying to find the best solution to the problem. Okay, prototype fidelity. So this is one of the places where it really comes, part of it just comes from experience. Some of it can come from a little bit of just extrapolating based on things you know about how materials work, plywood, whatever. If you've felt plywood, you know about how flexy it is, that sort of thing. And you're just kind of extrapolating, hey, if I build it this way, is it just going to break when I try to send a ball through it, or if I try to run it into something, or whatever I'm testing. But what we don't want to do, and what kind of the balance is, and where some of the prototyping experience comes in, is we want to be able to build it as quickly, normally in a, not necessarily as cheaply, but in a reasonable cost, because these aren't, it's possible we're going to have to build a lot of versions of it. It's not going to probably go on the final robot. We don't want to be spending too much of our resources on the prototyping process. But we do want to make it as close to reality as we can. So we want to make it very, very similar to what the real robot's going to see without completely building the real mechanism, right? We don't need to use the exact same materials. We don't need to use the exact same motors. We don't use everything that's going to be on the competition robot. But we do want to try to avoid anything that is going to make the results from our prototype not applicable to the competition robot. So there's this middle ground where you are trying to figure out what's important to be the same and what can you fudge a little bit in the prototyping process. So things that are normally going to be pretty important as you get closer to the final design is things like, are we actually doing it on the same FRC carpet that we use on the real field? So this is one of the reasons why the carpet in our lab, the bit that is carpeted, is competition carpet, is so that when we're in the middle of build season and we're testing something, we can just set it on the floor and know that the ball is going to skid around on this carpet about the same as it skids around on the competition carpet. Bumpers are a big one. So you saw in a lot of the different pictures we've shown so far, we'll bring out bumpers. Anytime we're prototyping an intake that's going to interact with a bumper, we want to make sure we're testing it with a real bumper. You don't want to just put a piece of plywood there that's not going to give, and the ball's not going to be able to compress into it. It's not going to be the same size. You want to put the actual bumper, get it up to the right height that you're going to be mounting your bumpers at. Anything you can do to quickly and easily make the prototype just a little bit closer to the competition robot, you want to do. Similar to being able to put the intake on something that actually moves, so either on a old robot chassis, even something as simple as like a furniture dolly. Like we've screwed in intake prototypes to a furniture dolly before, so we could push them across the floor. Because most of the time, if you just have a stationary intake and you're rolling the game piece towards the intake, that's a different interaction than a stationary game piece and you're driving the intake into the game piece. And that's what the robot's normally going to do, right? Or a rolling game piece and you're driving the robot at it. Very few games are going to have our robot just sitting still waiting for an intake or a game piece to come roll at us. Um, Same with a lot of the field conditions. This is a big one in certain games. Like this has been huge last year. If you only tested a 2020 robot or any infinite recharge robot with a single power cell, if you're like, oh, it intakes great, it goes right up into wherever we're storing them, it launches out of the shooter, this is awesome, everything's going to work. As soon as you put two power cells in that, the odds of it working are very slim. The power cells interact in all sorts of weird ways. They like to jam together, right? Once you put five, it's even worse. So if you don't test to the full field conditions of how many game pieces are going to be there, maybe there's other robots involved. Like we'll have, if you get, once we're at a full robot prototype, we'll have one of our old robots drive into it, make sure it makes sense that it's not tipping over, it's not doing anything else that we don't want it to. Whatever we can do to simulate the real field conditions, the better. The other part of that is integration with other robot parts. So we already talked about how we want to do integrated prototype sometimes when that part is important, or we even want to do a full robot prototype. So just figuring out, okay, how are they actually fed definitely matters. If you just build your entire launcher prototype or shooter prototype and you're always hand feeding balls into it, it's going to be a very different result than if you have a conveyor belt feeding balls in at a different rate with different spin, multiple balls going one after another. There's all sorts of little tiny tweaks that you may not think about, but we're always trying to consider, okay, what is different about this prototype than how it's going to be on the competition robot, and how can we either improve the prototype to avoid those differences, or do we believe that those differences won't matter? And if we believe that, why? Like this is definitely again an experience thing of, yeah, we're pretty sure this is going to be the same, or it's going to be similar enough to where we're okay moving forward to the next iteration of the design. What are the variables? So this is especially important for our optimization prototype, but it's also important just for the design of any mechanism anyway. We're always trying to figure out what are the things we can tweak and where are the places that we have to make decisions about our design. And which one of those decisions and little place and all different little settings and dimensions and anything else we're building into it, which of those are going to change the performance of the mechanism and the subsystem and everything, whatever we're doing in the entire robot, right? If we don't know what variables we're considering, right? If we don't think about things like intake width, roller diameter, motor speed, motor torque, anything that can possibly change between the prototype and the competition robot, if we're not thinking about those things and we're not trying to either make sure they're the same between the prototype and the competition robot, or at least know where they're going to be different and are okay with them, if there's some difference that we're not thinking about, that's often the difference that's going to allow the prototype to work and allow the competition robot not to. So we want to be sure that we've really thought it through of like, okay, this material is a little bit more stiff than what we're going to make the competition robot out of. Or maybe it's the other way. Maybe the prototype has more flex and the competition robot's going to be more stiff. How is that going to affect as the ball passes through it or as we launch a ball, whatever the system is? So the other aspect of that is some of the times, especially on an optimization prototype, part of the entire goal of that is to adjust a set of variables so that we can know how to design it into the competition robot. So it's possible that we're going to take that compression variable and we're going to be able to move the wheels in and out on the prototype. We're not going to be able to do that on the competition robot. And we're going to find a decent range or an approximate compression value that's going to work pretty well for what we want. Yeah, and the other part of that, like I already said, really is just, do the differences actually matter, and making some amount of a judgment to when they matter. And if you're not sure if they're going to matter, at least noting it so that when the final product comes, you can say, oh, this is why these are working differently. We need to adjust the final product in this way to get it back towards the results that we were getting that we liked from the prototype. Okay. And this is a little bit of an odd concept too, because we've just spent the last few slides talking about how it's very important to use the prototype to inform your decisions, which it's very true, but you're not going to get the exact right answer from the prototype because of what's happening here, right? There's always going to be some differences between the prototype and the final version, right? If there weren't, you've just built the final version. You didn't build a prototype. So because there's going to be differences, whether it's material, setup, whatever it is, your prototype's never going to get you the exact perfect specification for your competition robot, for your final version. And that's okay. We don't need it to get us perfect. The prototyping phase is to use the time and knowledge that we have, the time and resources we have, to get us the best starting point for our competition product. And a lot of times, the competition product itself doesn't need to be perfect. It just needs to be good. It just needs to do the job the way we want it to in a very reasonable time, whatever it needs to be. If the competition product does need to be perfect, if it's something where we really need to be able to like dial in this perfect shot trajectory for the launcher, or really worried about other things, we need to make sure we're designing in ways that we can adjust the competition product after we've built it. So this might be knowing that we can change the compression by moving the hood or like redoing a certain part of the robot to know that that's how we would change a certain variable. Or we know that we're going to be able to adjust the flywheel speed, and that'll allow us to change our shot trajectory enough to where we think we can get an accurate shot into whatever the goal is. Sometimes there's like tension and things that we can adjust. Roller grip or something, maybe we're going to be able to add tape to something to change the compression a little bit because we can make it a little thicker, or take tape off to make it a little less thick, that sort of thing. There's all sorts of ways that we can adjust the final product, but if something does need to be tweaked and perfect enough, we need to know that we're going to be tweaking and adjusting on the final product, and there's only so much you can do on the prototype because it's not going to translate 100% to the final product. Documenting prototypes is very important. The entire build process, everything we're doing now all the way into January, is a team process, and it's very important that we all are kind of gaining that knowledge so that we can have decisions being made across multiple people, right? Not every single person on the team, not everyone's going to make all the decisions, but it is important that we have enough of it documented that people who may not have been just happen to be paying attention or in the room at the same time can see kind of what's happening and why we're making certain choices. But also it's important just so that we have an idea. Build season moves really, really fast. We may test something on a Monday, and by Sunday we may have been, gone down some tangent, tried some bunch of different things over, that 7 days, and eventually hit a dead end and want to go back to what we had on Monday. And if we don't have it all documented, it's possible we don't, if we don't have good video, photos, measurements, anything we have, CAD, if we built CAD for whatever the prototype is, all of those types of things, notes written down about it, we may not know exactly how to get back there. We may not also be able to remember what we were doing. There's so much happening that just relying on your memory is not a good plan. So the more we can document, the more we can write down, the more we can kind of prove out our measurements and numbers, it's going to help us in the entire design process and the decisions we have to make throughout the process of getting our final robot into CAD and then produced as well. We do this in a few different ways. We have a really big slide deck that we call our design slides. We put pictures and notes every week and ideally daily about the things that we've been doing. I'm planning to redo parts of the way our design sheet works, but it's it's part of its goal is to be there to help document how a subsystem is progressing. We're going to see if we can make that a little bit easier. And then a big part of it is our photo gallery and our daily blog. A lot of the reason we do those things is so that we have this record and can go back and say, this is how we did it. Okay, what was different about this prototype compared to where we are now that it's not working anymore, but it was working back then, even though we tried to make it better and we made it worse. Like that happens sometimes. Sometimes you take a step backwards and you learn something there too, because you're like, oh, I thought that would be better and it wasn't. And so that we have to go back to the old version and try something new to make it better, or maybe that's as good as we could get it, and decide if that's acceptable or not, or whatever we're doing for that season. This next one is something that we do a lot of, but I don't think enough teams do. So I'm including it here, is definitely getting feedback from outside sources. When we're the ones all building it, and when we've spent, 8 hours on a Saturday getting something together and it finally works, it's really tricky sometimes to decide, is what we're doing actually worth it? So we'll bring in people who may not have been as involved in that prototype from our own team. So we'll ask them, hey, look at this. Anytime we have kind of like a milestone in a prototype process, when it's, it starts intaking balls, whatever it is, whenever we're kind of testing the prototype, we'll normally flag everybody in the room, tell them to come watch it anyway, because it's cool to see stuff work. And it just kind of gives everybody an image of where the robot's going and where each subsystem's kind of progressing. But we also want to get even further outside opinions from other teams who have been doing stuff, showing them how kind of the direction we're going. And so that's one of the reasons why we do the blog, and it's a really good benefit we get from it. We do have to know when we post stuff publicly, so we post a lot of things on the blog and on Chief and everywhere else, that we have to scrutinize the feedback a little bit, because a lot of times the people giving the feedback may not know as much of us. They may not have done as much prototyping as we have done. Their opinions and ideas and design ideas might be wrong, and then we have to choose whether to accept the idea and change something, or basically ignore it and move on. And so that happens a lot, because there's a lot of differing opinions. We'll get them from a lot of different people. We got ideas from teams from all over, and we kind of present them and talk about them most of the time and decide whether it's something that we think is useful and important or not. The same thing is true even if somebody tells you, this idea is great, this is going to be awesome. They may not know that it's going to be awesome. They may like the idea. Normally, if we've prototyped that far, we probably like the idea too. We've had a lot of things that we prototyped pretty far. Some things made it all the way to the robot that were not great ideas, but they went all the way through. So ideally, we want to try to get as much of the prototyping through multiple eyes as we can, and then use that information as well as part of the process, but not just relying on it, because again, we're the ones that have to go through the whole season with it, and those choices are still on us no matter what. This is just part of the process, is getting some outside feedback. Another part of this is, I don't believe, and what we've done over the past almost 11 years now, is that there's no real reason for the vast majority of FRC teams to keep any designs a secret. You don't really benefit from it. Other teams can use designs that we've made, and honestly, we benefit most of the time. We have had multiple seasons where some design we did, or intake or whatever, is used by multiple teams, and they come back and share with us ways that they've improved it, and it's made our robot better. It's been unbelievably valuable to our team to have a lot of our design stuff out in the public and getting feedback from there. Okay, tools and parts. So this is where we're going to talk about some of the things that we use specifically for prototyping, and most of the time these things aren't going to end up being used on the competition robot. So one of the most useful prototyping tools, especially early on for any sort of like concept prototype, anytime we're just trying to figure out how stuff works, is just a cordless drill to act as the motor for whatever shaft we're spinning, right? So many of the games in FRC need some type of intake. In general, some sort of spinny wheel intake is going to be better than any sort of clamp, claw, whatever other type of intake you want to build. And so because of that, a drill works very well to spin things. That's basically its only job. So being able to connect a drill to a hex shaft with some wheels on it. So that's what's happening here in this picture. We have one of our students holding a drill. This hex shaft has a bunch of wheels, and we were able to just like test an intake relatively quickly just by building up a little structure and having this drill spin. So there's a whole list of ways that you can get a drill connected to a roller or a hex shaft or anything else that you're trying to drive for a prototype. We have all of these options available in the lab. Which one we pick is just kind of dependent on where we are and which one's nearest and what the person designing the prototype likes to use. They all work basically the same. They let the drill spin the shaft, and that's all we're trying to do. Most of the time, this is going to be a lot faster than trying to fully mount a actual FRC motor, gearbox, belt, whatever it is that we need to do to get it working in that way. The drills are often just faster, so we use them for any quick prototype where we just need to figure out if this idea is going to work at all, or if it has where we think we can go next with it, or whatever we're doing. A couple other platforms that we have. So a pneumatics test panel is very useful. This is one of the projects that it's been on our list to build a new one for a while. We probably should design a new one. But basically the idea is that you have enough of a pneumatic system that you can charge an air tank. There's little buttons on some of the solenoids, so it's relatively easy to push them in, and you can swap which air it is. So if you have some mechanism that is going to be pneumatic powered on the robot, you can build a prototype with it and use the pneumatics to actually actuate it in the exact same way that's going to be done on the robot. And so hopefully you can learn in as much detail about how the cylinder mounting locations are going to work and anything else that we're trying to test. Because sometimes we just don't know like there's different ways to do it. Prototyping is one of the easier ways to do it, where if you're not sure if you got the math right that says, yeah, this cylinder is going to be able to lift this or whatever it is, testing it in real life and getting pretty close on the prototype is a good way to reassure yourself that, yeah, this is actually going to work. Another things we do is we'll have some amount of spare robot chassis. So we'll have things like a leftover practice bot. Maybe this was like a fall prototype from 2019 that we were using in 2020 to help test things. They're very useful for testing intakes. We needed this actually to test driving over the bumps that were in the 2020 field, so we used the test chassis to be able to do that. It has a big kettlebell to help weigh it down. This isn't super heavy, but it was 70 pounds or so. And so it was good enough for a lot of what we needed to test with. And we had some mounting points for intakes and anything else we needed to do there. Yeah, anytime where we need to have part of the robot or whatever we're testing drive into a game piece or drive into something else, having a movable chassis is super useful just to mount on top of. So an old robot, if you have a whole spare set of electronics or you have multiple, whatever it is, you can get something moving and running, and it makes the prototypes just that little bit more fidelity, so they're closer to the real deal. Proto Pipe. So this was something that we worked on in the fall of 2018, I believe, is when we first started this. I think that's right. And we have, it might have been the fall of 2018, right before the 2019 season. I think that's right. So it basically just uses PVC pipe. We wanted to make something super cheap, something that we could just print parts for and create kind of the structure of the prototyping. We had motors and wheels and stuff are pretty easy. Drills and stuff are pretty easy. But building up structures is sometimes a little bit trickier with prototyping, and it can take a little while. If you're trying to do it out of wood, you have to drill a bunch of holes. It's okay sometimes, but we wanted to figure out something fast, and this works for some of the prototypes that we're building. So this was a structure to build this was a prototype we built of a 2010 ball pinch roller mechanism or whatever. We had a couple drills spinning some pipe. So this costs very little. 3D printed pipes, the PVC pipe here is like $3 for 10 feet. It can be cut really fast. It's just like wood screwed together. Everything, there's some clamps so things can be adjustable and you can slide things up and down and clamp them down. So a lot of it was just being able to build something that allowed for quicker adjustment as we were first learning about the systems we were trying to build, and just allowing almost to the point where it's almost like it's not quite a Lego kit, but it was like the idea is just to give um, enough relatively cheap and fast construction methods to where we can have multiple people kind of playing around with ideas and just generating and just learning more about the problem in the first few days that we have it. So before we have to do a lot of CAD, like sometimes we'll lay this out in like some sketches or something in CAD, but you don't have to do a ton to figure out, okay, I need some different bars across here, and we just grab some of the connectors. So this is one of the things we're going to look at when we do prototyping training on Saturday, is how we can build some things with Prototype or Proto Pipe. There's a full document on Proto Pipe. It has a bunch of other examples of different builds either we've done or things that we have. Yeah, so the things we've done in the past. So this was a 2019 prototype that was built after 2019, I believe. Um, there's a variety of other concepts. Some of these are also tools that we're going to talk about up here in a second in the prototyping thing. I was actually looking for this picture earlier and I didn't have it. So we'll talk about these in just a second. And these are some of those shafts actually that we talked about earlier when we're talking about using a drill to prototype. You can lay down the ends of the shaft, so then you can chuck the round end into a drill, and you can spin these with a wheel on it or whatever you need to do. Yeah, and it goes through what all the variety of connectors and other things that are in the system. There's too many parts. This is a little bit, it works. There's probably some tweaking we can do to it to make it a little bit better. But there's a lot of stuff in there depending on what you're trying to build that you can relatively quickly print out and make a system that does work. There's motor mounts. There's all sorts of stuff in there that works relatively well. Since we've had this, there's been a couple other developments that other teams have done and other people have done. One of them is called Hype Blocks. So this is some 3D printed designs that 5254 and one of their mentors, Max, I believe mentor might be alumni, not really sure. Max worked on and published, and the whole team worked through. And this is very cool. It allows you to clamp onto a 1x1. So this was released right at the beginning of 2019. We used it in 2020 to build our prototype launcher. So we were able to we were able to like change the wheels out up here. We had these clamp blocks so we could change the spacing with belts. We made a hood. And so you can do a lot of different things with launchers and any type of motor mounts. It's definitely stronger and sturdier than doing the same type of thing with Prototype. And you can get a little bit more fidelity than you would with the Prototype system. To add on to that, Ryan Doigno made quick build blocks, which are basically kind of plastic 3D printed gussets that you can use to clamp onto the tube and make structures out of. So there's a bunch of them are all like the same size and shapes as some of the metal gussets that you can buy in FRC. And these take some bolts in the corners so that you can clamp on. So in theory, instead of having like the wood here, we could have had another gusset running across here to strengthen this up and square up the frame, maybe one across here lower somewhere. So you can just kind of make entire structures instead of having to kind of just have these rails like we did here. If we don't want to like cut more tube and drill, you don't necessarily have to. We drilled some holes down here. This was just into a 2x4 frame. Sometimes we'll add in some 2x4s and stuff to the structures, whatever works for getting the details that we need in the prototypes. From these, we spent some time, and this is something that I worked on 2 weeks ago, relatively recently. We haven't tested this very much, but it's another thing that we're going to play with this Saturday and see how well it works. And it's kind of a combination of these quick build blocks, the hype blocks, and some parts of Prototype to give us something that's able to print really fast. So we wanted to have something that doesn't use a lot of filament. It doesn't need any additional hardware, so you don't need any nuts or bolts or threaded inserts. You don't need any nuts. You do need bolts to do the clamping, but they thread right into the printed parts themselves. You can mount motors. You can put them onto the VersaFrame tubing, and they have kind of like a hole pattern, so you can adjust every half inch. So if you want to get something pretty close to a real dimension, you can. This block here allows us to do right angle or T connections, either one. and it should let us do some amount of prototyping relatively quickly. They're definitely lighter duty. They're probably not very reusable. You're probably only going to use them for a season and then have to like throw them away, or maybe be able to salvage them for certain things. But they're definitely less plastic and less print time than some of these other ones. But they kind of serve the same purpose. So hopefully we'll be able to utilize these well for some of the prototypes that we want to make as we're testing stuff over the next couple months and into next season. Some other things that are very useful while prototyping: any sort of cheap material. So we'll use plywood, 2x4s, masonite, also known as like hardboard, um, spare scrap plastic stuff that we have lying around, old robot parts. We'll use a lot of old rails and parts from bits of robots that we have in our scrap bins. Entire scrap field elements have gotten put onto robots before, or onto prototypes before. If there's young teams watching this stuff, ask old teams if they just have bits and pieces and parts that they don't want anymore. And most of us have just big piles of junk that we're willing to give away, that we've been storing for way too long. A lot of times we're going to clamp different parts of prototypes. So like this whole launcher mechanism, we just mounted some rails to our. This was a part of the 2017 launcher that we adapted to be able to shoot the 2020 ball, and so we clamped this onto this wooden cube that someone had built. We call it the Proto Cube now because we use it for a lot of prototyping. It's just a nice frame that you can mount stuff to. So we just clamp that up there. We'll use sandbags a lot. We have sandbags from when we do some event production stuff. We have to hold screens down or speaker stands, whatever. We take those sandbags and we use them to hold the prototypes down, so we're not having to like physically hold them down all the time. I talked about furniture dollies earlier, about having to make a moving prototype. A couple different ways to get motors to run. So this board back here, I have a picture on the Spectrum Prototype page actually. So this is the one this is actually ours. I don't know why in the presentation I don't have the correct photo, but this is the board that we use. So this board can take a battery, it has a main breaker, and then these 3 speed controllers are all controlled by a PWM generator. So these can all be controlled forward, backwards, and we can kind of set the speed. So if we're building like a launcher prototype, we can control 3 motors at the same time, give them the same amount of power, or same amount of voltage, and we can get a good idea of how the launcher is going to work. So that's what we were using here to drive these 2 motors at the same time, maybe 3 motors. I think we added a third. So we could do all of that testing. So that's kind of what we use instead of this little board that's here. For the motor test drill, or some people call it a phaser. On our team, it's gotten the known flight stick. I'm not entirely sure where that came from. I don't really know why, but that's what we call it, or it's what we have called it in the past. And basic idea is you just connect either a drill battery, so sometimes you leave the drill able to take one of the cordless batteries that we already use, or some people are modified to where it can plug into an FRC battery, and then you just have outputs that you can plug into your motor, and you can drive it with the trigger from the drill, and you can switch direction, control speed just on how it's pressed. It is important to know you can only do this with brushed motors. So any of the newer brushless motors do not work this way. So you can't do it with a Neo, you can't do it with a Falcon, you can't do it with a Neo 550. But any of the older motors are totally fine to work this way, and that's normally what we're using for prototypes anyway. Most of our prototypes are going to be powered using a planetary gearbox, like a Versa Planetary, or a sport gearbox possibly. The Versa Planetaries are our go-to for prototyping because we can change out the gearing, we can change out the output shafts, we can change out the motors, all relatively quickly in the same setup. So we have a lot of different bits and pieces of the Versa Planetary ecosystem or parts, and we can add them all up to kind of get a pretty close approximation of how we'd want the actual competition mechanism to work. Most of the time in prototypings, we're going to use 775 Pro motors. They're a little bit older. We have quite a lot of them. They were super useful before the brushless motors came out that we normally use on our competition robots now. So we have a lot of them around. They can work with the drill testers and any of the boards and things like that. They're relatively small and light, which means they're not as heavy as some of the other motors you could mount up, and if you're using on like lighter materials or 3D printed parts, these are nice because they're not going to bend or break any of our other light materials. And they work pretty well. They have quite a bit of power. so they're not underpowered compared to what we're actually using with brushless or anything like that. So they allow us to test really well. So this is mostly what we're going to use for building prototypes. If we need to do something with a if we need to do something with a actual velocity control, or if we need to get data back from the prototype a lot more, powering it with a Neo and a Spark Max can let us do that. So the Spark Max's USB port allows you to plug a Spark Max directly into a computer. You plug the Spark Max into a battery, and then from there you can control the Neo and give it full control loops, so we can have it set to a certain velocity. So if we're trying to test a shooter, we can know that it's actually getting velocity control. We can get back data about how much current is being pulled by the motor or how fast it's spinning, anything like that you can't do just from a basic 775 Pro. So this is definitely useful if you're trying to do a little bit more advanced prototyping. Something like this is useful. If you want to do the same thing with a Falcon or a Talon SRX, you have to have a full Robo Rio setup so that you can communicate to the CAN bus and everything else. That's just a little bit more work. You can get a little bit faster with the Spark Max. A couple other things that we'll use. So sometimes we'll use VersaFrame because it already has the holes drilled in it. So depending on how quality or how the exact dimensions we're trying to make with the prototype, having those holes and gussets and things, we can make something a little bit closer to real life. Similar, if we need something a little bit stronger, there's Rev Extrusion allows you to have these rails that you can slide the nuts through. So if you need something, a relatively rigid and strong prototype that you can slide back and forth, and you're not sure how the spacing of things are going to work or exactly where a motor needs to be to slide and connect a belt or something, these work pretty well for that if we don't have the clamp blocks or whatever else we're using if we're not using a 3D printed thing. So these are just some more examples. Normally we're not going to use these as our early prototypes, but as we're getting closer to real stuff, we'll sometimes bring these out to meet a need that we have with whatever the prototype is. Okay, a couple things, then we're going to look at examples for a few minutes before we end here. So one of the other tools that we use while prototyping is being able to take high-speed video of our prototypes. So there's a lot of times we're going to be looking at them and seeing how they're interacting with the game pieces or themselves, and we want to be able to look at details that we may not be able to see in real time. So taking slow-mo video, even just with an iPad or something, gets you close. One of the new cameras we bought can do even higher frames per second. I don't remember exactly what it is, but it's much higher than 120, so we can slow it down really, really slowly, and we can see frame by frame exactly what's kind of happening in the mechanism, so then we can know what we need to tweak for the next version. Things like flex or vibration in the shooter and things are stuff that's just really hard to see in real time just with your eyes, where you can zoom in really tight on a slow motion video and see exactly how something's moving. Any video in general is really useful if we want to see like the pattern of balls coming out of a launcher. If we have video, you can slow it down frame by frame and see exactly where the balls are going. It's all very useful in analyzing the prototype and making our final product better. This is one that we haven't done much of, but other teams have used it very successfully. So you can build scale models. If you can get if the game object or whatever you're building happens to be able to be scaled down relatively easily, and you think you can get something to approximate the physics and mechanics of whatever it is at that smaller size, building it smaller allows you to build things much faster and take up less resources. So in 2017, where we had to sort all of those wiffle balls and launch them all out, 125 has discussed, Neutrons have discussed how they built all of their kind of hopper prototypes at golf ball scale instead of the 5-inch ball scale. So they're able to basically do almost like they're able to print the entire thing up on a single print bed, have a much smaller version that they can test exactly how the balls are going to play and interact. And we're able to build up these scale prototypes super quickly because they're so much smaller. And then as they iterated from that, moved up to the full size and already knew so much about the problem because they were able to experiment really quickly at the small scale for the problem. Okay. I'm probably not going to go through all of the examples here. They're going to be in the slide deck and we can watch some of the videos. I did want to put a couple more examples of things that we've done in the past and some very kind of famous examples of full robot prototypes that other teams have done. So this is just an intake prototype from 2020. We showed it earlier from parts of it and like how the drill was used. but this was just to see, maybe does this work? We hadn't seen anything that allowed for like a kind of bigger space with more than one ball in the middle, and we were just kind of playing around to see what it looked like with these vectored intake wheels back here, and just kind of how all of that went together. We ended up not really using this design, but that's kind of why we prototype, is we build something to give us enough information to decide, do we want to continue down this path or not? A lot of the goals of prototyping is actually trying to prove something wrong, not prove something right. We're basically saying, okay, how much do we need to build to prove that this doesn't work, or isn't going to work well enough for our needs? Like, a lot of what we're trying to do is just get rid of ideas, not necessarily just prove that something can work, because a lot of things are going to work. We're trying to figure out what's going to be the best and most optimal one. So getting rid of things is more helpful in that discussion most of the time. This is another more fully functional prototype. Part of this is just to show that we have it on another bumper again. We use like masonite cut out on the laser cutter, so relatively quickly. I think these are rollers that we had from the 2019 setup, so we didn't like have to make our own rollers again. We already had these, some 3D printed clamped connectors, I think, that were already done also from 2019. So these are just like parts from an old robot. We threw some wheels on it to change it up a little bit. So this was done in CAD, so we got some of the spacing right, some of whatever belts we had, pulley we had, that sort of thing. But it doesn't have to take very long to make a pretty functional intake with kind of parts that we already have. We're not having to build everything to test our concepts. Our 2020 launcher was similar. This is the part we didn't show earlier. So the hood here was built to be adjustable, so we could move it in and out, so we can change compression. It was built to flex in a certain way, because we really weren't sure how tightly we wanted to squeeze in on the launcher wheels, so we were able to test with that. It was using Neos attached to a old robot chassis, so we had a full Robo Rio, so we were able to write the software to be able to control the Neos up to a certain speed, so we knew what velocity we were launching them at. We had a different Neo launching like the accelerator wheel compared to our main launcher wheel. Some of the sandbags I talked about earlier, so those there to stabilize it. We were shooting into the goal we had built, so we were kind of figuring stuff out with this launcher. One of the things we talked about earlier about fidelity and how close things are to the real robot and where that causes problems, this was one of the biggest problems we had in 2020, was this prototype hood wasn't anywhere near as rigid as our production hood ended up being. So because this lip right here at the end, basically as the ball was coming through, this could bend up pretty sharply, and we never really noticed it while we were testing. And that became a huge problem, because we built our production one to be the same angle. Everything was working fine. Balls were going in the goal. We were very happy. When we built the production hood, the balls started shooting way too low. They were basically going just almost in a straight line out of the robot. And we didn't know why. And it was just the difference in the flexibility of this hood was allowing the ball to come out at a much steeper angle than our production hood could. So that was a point where we didn't analyze the fidelity properly and set us back pretty far in our production hood, where we had to kind of almost just guess an angle. We didn't have a lot of information, and make a new one pretty fast so that we could get back to testing and hopefully getting back in the correct spot. We were able to do it, but it definitely was a scary moment in the season, as we were pretty far into build when we finally got to test the production hood, and it didn't behave in any way like the prototype, and that's really what we're trying to avoid throughout this whole process. And this was a point where we weren't able to do it. We didn't do it well here. Okay, so this is one of the last videos we'll watch. So this is a very famous prototype by 254, the Cheesy Poofs, in 2014. They released Skystalker right towards the end of the build season. This is February 15th. So this is about week 5 or so, maybe week 6. I think it's week 5. Hold on one second. So this was basically their fully integrated robot prototype. This is not quite the same as what I think is a prototype robot that we're going to build. Ours is going to be much closer to the final specs. This is all 2x4s and just mounted on an old chassis. This is probably closer to an integrated prototype that just happens to be able to be fully mobile, because they definitely changed a lot of specifications as they went to their competition one. but this prototype was able to prove a lot of pretty much every concept that they wanted to with this design. The advantage here is that this is a rather humorous video. They did it in a very meme style, so it gets very famous. You can already see it's Chazzy Poofs, right? Chezzy Poofs. That's where the Chezzy Champs gets its name. I think they were using it on their team for way longer. But it proves a lot of the right ideas with the prototyping.
Return to the Mac, get up what it is, what it does, what it is, what it isn't. Looking for a better way to get up out of bed instead of getting on the internet and checking a new hit. Me get up, first shot, come strut walking. A little bit of humble, a little bit of cautious. Somewhere between like Rocky and Cosby's for the game. Nope, nope, y'all can't copy yet. Bad, moonwalking, and this here is our party. My posse's been on Broadway, and we did it all way. Chrome music, I shed my skin and put my bones into everything I record to it. And yeah, I'm on. Let that stage light go and shine on down. Got that Bob Barker suit game and Plinko in my style. Money, stay on my craft and stick around for those pounds.
So yeah, so you can see from just what we've already seen so far, there are a lot of things that are going to be different than on the competition robot, right? They just have like this pneumatic kicker here that's a little bit different than what they showed a little bit earlier. The wheels are changing, so they're pretty constantly iterating this design, and we're seeing different bits of it in this video. But by having this fully integrated prototype, they're able to test through and see all those concepts to get to when their final design works. They have like, closer to a real intake, has a lot more of the real FRC parts. The ball feeder in this picture was definitely not what they put on their real robot. Same with like the hood or anything else. But they got the idea across. It's able to score points, right? If you built a good version of this, which there was actually a team that did build a wooden version of this they actually played the 2014 game in a 2015 off season in California, and 973 came with like almost a wooden version of this same sort of design architecture and did very well with it. So you could do something like this if you needed to. If you didn't have materials to build it out of some other way to make it a little bit more robust or optimized, you could still see that this is a pretty good robot for the game. It's able to intake a ball, it's able to launch it through the goal, it's able to kind of do all of those things it wants to do.
Give that to the people, spread it across the country. Labels out here, now they can't tell me nothing. We give it to the people, spread it across the country.
I'm yelling timber, you better move, you better dance.
Here we go back, this is the moment, tonight is the night. We'll fight till it's over, so we put our hands up like the ceiling can't hold us. Like the ceiling can't hold us. Here we go back, this is the moment, tonight is the night. We'll fight till it's over, so we put our hands up like the ceiling can't hold us. Like the ceiling can't hold us.
Now, can I kick it? Thank you, yeah, I'm so damn grateful. I grew up really wanna go fronts, but that's what you get when Wu-Tang raised you. Y'all can't stop me, go hard like I gotta hit it with
most of it. Okay. So yeah, that's one of the more famous actual like full wooden prototypes. We normally don't get quite that far with just wooden 2x4s. Some years it's more than others. It kind of depends on what we're trying to test. But it's definitely something you can do where you don't need a lot of resources. They're just kind of drilling holes, getting bearings into the 2x4s and making it work. Some other teams have done something similar. So this is 1241s in 2016. This drivetrain wasn't powered, but it was very similar to what the final drivetrain would be. So they could like push it over the obstacles it had to drive over that year. But then the whole ball path was, so they could intake a ball, bring it all the way up, feed it into the launcher. You see parts of it are just, like, again, they have like some clamps down here. They have all, I don't know what's going on with my cursor. Okay. They have all sorts of just little bits and things that are fast build to test the full geometry of what was their final robot. This was a very good robot this year, and they kind of did a lot of it just with plywood, 2x4s, and all the such to be able to get it fully prototyped the way they wanted to. 1690 did another similar thing in 2016, actually. They were able to mount their intake up on some 2x4s on a driving base and kind of test the whole process of this robot. This video will be in here if you want to watch it in the slides. And they do a really good job of building something like that too, where if you did make some tweaks, you could build a competition version of this and it would probably do surprisingly well. But it was all just to make sure the concepts that they wanted to actually test, that everything was going to work together, kind of prove it out before they were able to produce the final robot.